So what's going on with galaxies? First of all, galaxies are really complicated objects when you think about it. Because in galaxies, you don't just have dark matter, but you have stars, you have gas, you have all kinds of physics, which is very complicated. So that complicated physics should yield some pretty complicated looking objects. But in fact, galaxies are remarkably simple. Their rotation curves, which I explained to you earlier, the velocity as a function of distance away from the center, as we've said, is flat as you move out. And that's pretty regular. We see flat rotation curves all over the place with galaxies. Why is that? More importantly, and this may be a little subtle, but it's a very important piece of evidence, there is a scaling relation, an empirical scaling relation for galaxies, which works remarkably well, and we don't understand why. This is known as Tully-Fisher, because of Tully and Fisher. But really, many people have contributed to this. So let me tell you what this relationship is all about. What is a relationship between v, which is this asymptotic flat velocity that you see in galaxies, the total mass in ordinary matter in the galaxy. And that precise relationship is that the mass in ordinary matter is proportional to this asymptotic velocity to the fourth power. Why is this strange? It's strange because if you think about it, the velocity asymptotically should depend on how much dark matter there is, right? Why does that have anything to do in such a precise way to how much ordinary matter there is? It sounds like a conspiracy, right? The ordinary matter is a small component, and yet it dictates precisely the amount of dark matter there has to be further out in this precise way. And you see on the plot, it's a very tight relationship, okay? And that's not understood. But as I said, it's a complicated process. You have to model, if you're going to try to model this in the computer to understand where this comes from, what people do is the following. You assume ordinary dark matter that doesn't interact with itself. You can just think of it as just interacting through gravity, doesn't interact with ordinary matter. But you put on your computer that simple stuff with all the complicated stuff of stars, of gas, supernova exploding, black holes. This is just a partial list of what modelers have to put in their codes to actually simulate a real galaxy. They have hundreds of parameters, okay? It's a very complicated system. Now, what they do with the simulation is they actually choose those parameters in the best guess possible, but in a way that they can reproduce this beautiful Tully-Fisher scaling relation. The key point is the following. You see, if you go back to this Tully-Fisher relation, what was striking about it is not the fact that there is a scaling relation, but it's the fact that it works so well. In other words, it's so tight. You would expect, maybe on average it's this particular slope, but you'd expect points further out representing the fact that there's complicated physics going on and it's not a perfect law. Whereas here it looks like almost it's perfect. And so indeed, when people do simulations, they find that the dots are the simulated galaxies, so with all the complicated physics, and what you should compare it to is the yellow band. The yellow band is observations, if you want. So what you see is striking. You see that the simulated galaxies are all over the place compared to this thin band which represents observations. Okay? So there has to be a conspiracy, in a sense, to explain this. There are other problems, and people disagree. Are they problems? Are they just, again, misunderstanding what the complicated underlying physics is? Let me mention a couple, and as I say, these are a matter of debates, but one of them is the so-called missing satellite problem. When you do simulations of dark matter only, I showed you one, with all these beautiful structures and these clumps, what you find is the following. You find, you see on the left side, this is a simulated dark matter story. You see a big dark matter clump in the middle. That would be the home of, let's say, the Milky Way galaxy. You imagine this would be the home of the Milky Way. But you see surrounding it are these hundreds of little clumps, okay? And you wonder, those should also, in principle, be homes to smaller galaxies. So when we look around the Milky Way, we should see hundreds, in principle, of these small galaxies. And we don't, okay? We observe 30 of them. Now it becomes a question, maybe those guys, these lumps are there, but they were too feeble to hold on to their gas and to form stars, so they lost their gas. There's a whole story you can say. And this problem, one can make it even sharper with technical details. But anyways, it's one of the puzzles that's been around for quite a while. Secondly, you expect that around a Milky Way-like galaxy, notice that all these clumps are pretty much isotropic, right? They look pretty much the same all around the Milky Way. Whereas what we observe is quite remarkable. The satellite galaxies, so on the bottom plot here, I show you our Milky Way galaxy at the top, with the blue dots are the dwarf galaxies, the satellite galaxies around the Milky Way, those we observe, and those around Andromeda, our nearest neighbor, with its own satellites. And what do you notice about them? You notice that the galaxies that we observe, they're not isotropically distributed around the Milky Way or Andromeda. A number of them lie on these planes, these thin planes. Okay? And moreover, the Andromeda plane points towards the Milky Way. This suggests at least there has to be more physics than the simple picture above of just these clumps individually happily forming around the Milky Way. So these are things that some of us spend a lot of time thinking about. It's, again, it could just be conventional physics at the end of the day, but it's at least puzzling. Okay, so here's the bottom line. In my mind, this is not just conventional physics. It gives us strong hints about the nature of dark matter. Okay, so if you want, I think nature is singing for us, loud and clear, and we should be listening to what nature has to say about this. I want to tell you about a crazy idea. Totally radical idea, but at the end of the day, I want to tell you how I think about this idea. And it's called modified Newtonian dynamics. So this is a law that was proposed by Marty Milgram, shown here, an Israeli physicist, who proposed it more than 30 years ago. He studied galaxies, and he proposed this rather bold idea. So after all, when we say in the galaxy there has to be dark matter, we base that on the fact that we see stuff moving faster around the galaxy than it should. But we only infer this based on gravity. We don't see the dark matter directly. We infer this on... So what if, instead, there was no dark matter, but instead our law of gravity has to be revisited? Here's what he proposed. He proposed, okay, let's imagine there's no dark matter, and instead, Newton's law of gravity has to be altered when you go in a particular regime. And here's how it looks like as an equation. The statement is that when you transition to this new regime beyond Newton, it's when you go to very low acceleration. Okay, so that you have to think about it, right? Acceleration here, 10 meter per second squared, okay? This transition occurs at extremely low acceleration. You see the numbers, 10 to the minus 8 centimeter per second squared. That's all you need. That's the acceleration you need to keep a star far away in orbit in the galaxy. When you transition below that scale, all of a sudden, Newton's law of gravity gets modified. Instead of being the Newtonian acceleration, you see this particular square root form. It's the geometric mean of the Newtonian acceleration and this new characteristic acceleration. This sounds totally kooky, okay? But it's, if you want, at the end of the day, it's a proposal, okay? So he goes ahead, makes this proposal, and starts looking at do galaxies actually obey this? And amazingly, they do, okay? So here are some fits, actual fits of real galaxies, their rotation curves. And with this simple law, there is no dark matter to muck around here. You have a law which only involves the stuff you see. And with that stuff you see, you predict how these rotation curves should look like. And you only have basically one parameter, which is this characteristic acceleration. And it works remarkably well. Okay? Furthermore, this Tully-Fisher relation that we observed is an exact prediction of this theory. Exact prediction, okay? And I could go into details. Actually, this sounds like a post-diction in the sense that, you could say, well, he cooked up a law that fits those rotation curves. Not so. He actually predicted that some galaxies, in particular, if you look at the bottom right corner, that galaxy was not observed at the time where he made his predictions, when he came up with this idea of MON, and he actually predicted that such galaxies should exist. Now, you can take different viewpoints on this. The conventional viewpoint, we have to distinguish empirical facts from theory. As an empirical fact, this works. So even if you believe that dark matter is this conventional particle that doesn't interact, blah, 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 your viewpoint is that I put in this simple particle, I put in all the messy physics of stars and gas and all that crazy stuff, this ought to come out. It has to come out because it works with the data, okay? You see what I mean? So you could say the extreme viewpoint is that, no, there is no dark matter. This law is fundamental, it's a fundamental law of gravity, Newton was wrong. Or the conventional viewpoint is, there is dark matter, it's a simple particle, and somehow when you put in all the complicated physics, this comes out. But it has to come out as an empirical fact, okay? this is not all roses, unfortunately. That law that was proposed by Milgram works beautifully well with galaxies, but it fails on other scales, which is why a big portion of our community chooses to basically ignore it, because it fails with these other pieces of evidence that I presented you as members of the jury. In particular, galaxy clusters doesn't do very well with galaxy clusters. And when you get to the cosmic web or the cosmic microwave background, also doesn't do very well on those scales, okay? And as I said, this was to me the DNA evidence for dark matter. So if you're going to mess around with microwave background in this cosmic web, as members of the jury, you start feeling uncomfortable, very uncomfortable. But as I said, it's true. That empirical law works for galaxies. I take the middle ground, okay? I'm in the middle. I don't think it's a fundamental law of gravity. I don't think it's purely some magic having to do with stars and cooling and supernova and stuff like that. I think it's telling us something about dark matter, that there's a property of dark matter that is such that this MON phenomenon arises in galaxies. So I take the middle ground. I think there is both dark matter, and I think MON, this modified Newtonian dynamics, is also there, but it's due to the fundamental properties of dark matter itself. So how do you do that, right? It's easy to say, but how do you put the two together? And in fact, you know, as a scientist, you already should have pause at that moment, because if I tell you I have two phenomena, MON and dark matter, and I'm going to put them together, you should start saying, well, okay, wait a minute. It sounds too complicated, right? Why can't we just get away with one? The proposal that I've been thinking about, and this is what I want to share with you, my research has been to think about the physics of superfluidity as precisely the ingredient that marries the two in a natural way, okay? So this will be a unified approach to both this modified Newtonian dynamics and dark matter through superfluidity.